well. It's not a multiple of 10. It's 7 days. Same for a minute. We haven't gotten rid of a minute. A minute is 60 seconds. It doesn't fit really well in the metric system. In fact, it has now become officially part of the metric system. The minute being 60 seconds is a unit in the metric system that is not a multiple of 10. It's just because of human history. And it's useful. And I would say the same thing here. We have human history, but more than that, we have usefulness because a lot of our stuffs are things like coffee and tea and milk, which is like 99% water. And so when we go to calculate their energies, calories are really nice to use. All right. So again, this is a long way of me saying that we're going to be using two different units of energies, calories as well as joules. And we need to switch back and forth. And so there's the conversion factor. And so we're going to do that quite a bit. Now, the other two units I will mention a little bit. We won't be really using them for this class. As I said, another unit of calories has a capital C. And the reason I wanted to point that one out is because the one with the capital C, right here, is the one that a nutritionist would use. So if you swung into McDonald's for lunch, and you get this Big Mac meal and fries and a shake, and you look on the menu down there, it's ridiculous. It probably says, hey, this meal's going to be 2,000 calories, which is the total you're supposed to eat for the whole day. You're like, okay. But they're not talking about this calorie. They're talking about this calorie. Now, this big calorie is related to this calorie. And so when a nutritionist are talking about a calorie, they're talking about the big C. And that's just 1,000 times bigger than the little c. So in the metric system, it works better for us to call this a kilocalorie. And so if you want to talk about a lot of calories, and you are talking about 1,000 calories, let's just call it a kilocalorie. So that's why we in science don't use the capital C, because we've got the prefixes of the metric system. It also is a nice way to say that if you were told that keep your food intake down to 2,000 calories, well, you guys are young, so maybe that's a little low for you, but for us older people who don't have a metabolism still working and don't exercise like we should, this is their recommendation, 2,000 calories or less. But what they mean by that is the capital C. And so if I do my unit conversion, this is then 2,000 calories, and in place of calories, let me put 1,000 little calories. And so this would actually come out to be 2 million calories. So if I'm going to use a description of nutrition for me, but use kind of the science term here, I would use the lowercase c. And so I should keep my food intake, my energy intake, below 2 million little calories. If I eat more than this, because of conservation of energy, my body's going to say, okay, you didn't use that while you were walking around or running or thinking, because your brain actually uses a lot of calories. So you didn't use that energy, so what I'll do instead is I will store it. And so that's what ends up happening to me, is my body just stores that extra energy. And of course, not in the world we live today, but if we lived more in the wilderness, that's the whole point of our body, is to store that energy, like a bear, because it may winter way come around, you won't be able to find food. And so in order to survive, you will need that energy. And so the fat reserves is what you live on here. We live in a very different world, so it's not like winter comes along and I can't find a cheeseburger. You know, In-N-Out's still open in winter and summer, so. They were even open in the pandemic, so you know I didn't have any troubles finding a cheeseburger. Let me go one more step, because again I want you to see this unit conversion. So if I go to million, but I wanted to know it in joules, this is how I would convert it. I would replace the lowercase calorie with the 4.18, so 4.18 joules. And so this is a way of just kind of showing you the unit conversion, as well as reminding you all the way through this course that we got to go back to chapter 1 a lot and switch our units. And so if I multiply this out, that's an 8, double that is a 36. And so this would be 8,360,000 joules of energy. And so that's the normal amount of energy that really is appropriate for me. A given day, this is about how much energy I will use. That's why my 2,000 calories is really kind of the nutritional, and capital calories is kind of the nutritional value for me, because again, as I walk around and videotape, and as I think, and as I go home and play with the dog and do the dishes and make dinner and all those good things, this is about what energy I will use. And so if I eat more than this in energy, then my body will store it as fat. And of course, if I wanted to lose some weight, then I should take in less than this, because I'm going to use this much on a given day. And so if my intake was less than that, my body would have to get that extra energy. That's why we call it conservation of energy in the first law of thermodynamics. And then my body would grab it out of somewhere, which would be stored as fat right here, and it would suck that in. And so then I would use a little bit. And then if I did that day after day after day, then eventually there would be a noticeable amount of weight loss. In fact, 1 pound of fat is an amazing amount. It is, 3,500 big calories. So it's not quite double this, but just 1 pound of fat then is probably looking at about 16 million joules of energy. And so it's hard to get rid of 1 pound of fat. And I shouldn't keep talking about this, because it's making me think that I really should just stop eating so much so I could lose some weight. But I just, as I said, like my cheeseburgers, so I just don't follow that well. Now, let's keep going. How are we doing on time? A few more things here. We'll wrap it up here for today. But remember I said that there's another one here. This British thermal unit is very useful. Not that we're going to be using it, but like I said, you should be at least exposed to it. And it probably fits better if I write it right here next to this one. Let me write it right above here. So what is a BTU? Well, kind of like the calorie, it is the amount of energy, and I'll even write heat energy, needed to raise, and here's a special point, since we're talking about the empirical units, I wouldn't say 1 gram, I would do 1 pound of water. 1 degree, can you guess? Fahrenheit. And so the BTU is defined a lot like the calorie, except we're using the empirical units instead of the metric system. And again, it's just the amount of energy needed to raise. In this case, 1 pound, 1 degree Fahrenheit. Now, a pound is a little more than 1 gram, although a Fahrenheit is about half of a Celsius. I don't recall what the conversion is off the top of my head, so let me not try to give it to you. But for those of you who go into engineering, you'll come across this. In fact, I recently came across it twice this last couple of months here. One is, sadly, I go out one morning about a month ago and my water heater had busted, and the garage is half flooded and boxes are wet, and I was like, oh no, and there's no water. So I said, well, I guess change plans today. Let's get a new water heater. So shut off the water, pull out the old one, go racing up to Home Depot and start looking at the water heaters. And among other things, and the big thing I wanted was a 50-gallon water heater. Or years ago I had a 41 before this one broke. And when we switched from a 40 to a 50 or a family of 5, and it was just nice to have 50 gallons. And I was like, okay, it's got to be 50 gallons. So I go in there and I'm looking at them all. Okay, here's a 30-gallon, here's the 40 gallons. Here's a 50-gallon. Okay, we got to get a 50-gallon one. But as I looked closely, it also said 40,000 BTUs per hour. And that was the engineering. What that meant was the burners down below put in a heat of 40,000 BTUs in an hour. And the reason that was important is, well, how long will it take if somebody gets into the shower? And so if 2 of my boys and my wife get into the shower and use all the hot water, my question is, okay, how long do I have to wait before I have hot water again? It's 50 gallons. And if you do the math there on this 40,000 BTUs per hour and the 50 gallons, it's about 20 minutes. And so you should have hot water, depending on how hot you're going to warm your water, in about 20 minutes. And so that's really what it was designed to do. And so this water heater was a little bit bigger in terms of BTUs per hour than another one. And I go, well, let's get that one, because this one will only take 20 minutes before we have hot water again. And this other one was going to take 30 minutes before we had hot water again. And so that's why that engineering was related there. Oh, but also connected that, I went to get a new barbecue, and this wasn't a big deal. I was more interested in the size of the grill. Again, with my family, I just need to have 4 burners and a big side grill by the time we put all the hamburgers or hot dogs or chicken on there. But it also had listed the BTUs. It's BTUs per hour. This is the rate at which the heat put out. And so how quickly can it put out heat, which, like I said, wasn't such a big deal. But this gives me a chance to at least talk about a BTU and point out that, well, I should mention it, even though going here forward, I'm probably not going to say anything more about the BTUs. Now, I see our time is really up, but I'm going to take one more statement here so I can kind of finish this up here. But now that I hope I got across to you these 4 units of energy and the difference between internal energy and heat energy, let me point out what temperature is and is not. Because temperature is often confused with heat energy also, and it is not. Let me put this. It's related, not exactly equal, so let me just put related to, and here's the key word, the average kinetic energy of the atoms. You see, that word average is absolutely important here, because if I were to take a small bucket and a little bucket, maybe I'll do I have something that represents a bigger bucket? So this will be my big bucket here. So here's my big bucket. Here's my little bucket. Now, if I come over here to the sink and I fill them up and I put them here, I will have a lot of water in here, which means I have a lot of molecules. And I've got just a little bit of water in here. Now, it's still a lot of molecules because these things are so small. In fact, as a side note, if I fill this with water, there are more molecules in here than there are grains of sand on the entire Earth. Counting all the beaches and all the deserts, there's actually more molecules in this glass of water than all the grains of sand on the Earth. I'll even go you further. There's more molecules in here than all of the stars in all of the galaxies. I mean, there's something like, what, 400 billion stars in the Milky Way galaxy? And there's something like 400 billion galaxies out there. I think the latest prediction of the universe that we can observe anyways, because it might be further beyond what we can observe, but our observable universe has like 10 to the 22 stars in it. That's less than a mole. That's only 1/10 of a mole. Remember, water would be 18 grams would make a mole. 2 grams, this much water, has the same number of molecules as all the stars in the universe. So this glass of water right here has more molecules in it than all the stars in the known universe, plus all the grains of sand on all the beaches and all the deserts in the world. There are more molecules in here. Well, I got sidetracked, but that's amazing, the size of numbers we're dealing with here. So I said that because I hesitate to say there's a small number of molecules in here, because it's really not small. But it is smaller than this by a long way. There's a lot more molecules in here than in here. And if I were to ask you about the internal energy, I would get a lot more energy in here than in here. Only because there's more molecules. See, on average, they have the same. In other words, they came out of that sink. That sink, our water comes out, if you remember yesterday's lab, at about 20 degrees Celsius. And so I would say the water in here is 20 degrees Celsius. That's its temperature. I would also say here, the water in here is 20 degrees Celsius. They have the same temperature. That means on average, if I grab one atom, or excuse me, molecule out of this one, and I grab one out of this one, they each have about the same energy. Therefore, they have the same temperature. So they have the same average. That's why that word average in here is so important. The temperature is telling me what is their average, not their total. And that's why this word and this word are easy to confuse. Temperature is not the total energy. Temperature is related to its average. So if I had one molecule and I told you its temperature is 20 degrees, I could tell you the energy of this one at 20 degrees, but to get the total energy, I would have to multiply it by how many molecules I have in here. And that's why it's different than this number. Same temperature, different total energy. It may even sound funny, but I think this is one of your homework questions. It says something like this: which has more energy? This cup of hot water, which I don't have any water, but pretend hot water, or that really cold iceberg in the North Atlantic, that giant cold iceberg. And what you're supposed to get out of that is, wait a minute, that iceberg is really cold. So on average, the molecules are moving very slowly. So if you just randomly picked a molecule out of the iceberg, it would have less energy than one molecule randomly picked out of my hot water. And so when I compare 1 to 1, or if I compare the average, this has a higher average. This has a higher temperature. This hot water might be at something like 70 degrees Celsius. But the iceberg, which has a lower temperature, its temperature is probably around 0 degrees Celsius, has a lot more energy. Only because there's so many molecules in there. One more example, we'll call it quits. If this was face-to-face, I would say something like this: that because you guys are students, most likely, not always true, but most likely, I probably have more money in my wallet than you do. However, you guys collectively probably have a lot more money than I do. So if you look at me and take my average, and you look at the average you guys sitting in this room, if you were sitting in this room, probably on average each person only has $2. But there's 60 of you. So on average, if you have $2 and there's 60 of you, you guys together have a total of 120. And I don't have that much. I only have $10. My average is $10. Your average is 2. So in other words, my temperature is more than your temperature, but you actually have more money than me. And that's that subtlety between what is the total versus what is the average. So be careful with those 3 words, and it's time for me to wrap it up here for today. I get all excited on this and I'm way over time here. So let me just say bye for now, and I will see you tomorrow.